So we go on to the last topic in this section, and that's called combining power series. But before I talk about it, let me explain and bring up something that we saw before. So suppose you have a power series x to the power k, k going from 0 to infinity. Now this is our good old power series 1 plus x squared plus x cube plus so on. Now we know that this is like a geometric series where it would add up to, so it converges and it adds up to 1 over 1 minus x, just like this adds up to a over 1 minus r. A is 1 here, r is x here, so it adds up to this, and this is of course as long as absolute value of x is less than 1. So what we have here is the interval of convergence is between -1 and 1, open interval. You know the meaning of interval of convergence now. So all values of x between -1 and 1, this power series converges to this. Now you notice that a power series is a function of x because it's got x in it. So when it converges to a function of x. So some function of x. Now it's not very frequent that we know what this function is going to be, because if you notice in the previous examples, all that we could do was find the interval of convergence. We cannot find to what function it converges. But in some series, for example this simple one, we can find this function. So in other words, any power series that converges to a function of x. It's just that we don't know what that function is. Okay, so let's go to this theorem. It says suppose the power series ck x to the power k and another power series dk x to the power k converges to f of x and g of x respectively on an interval I. So this is the interval of convergence. Then what it's saying is that if you add or subtract these two series, then they will converge to f plus minus g. Obviously, because if this one goes to f and this guy converges to g, then if you add them, then you will have addition of f and g. The second one is multiplication by a power. So what it's saying, you can read slowly what it is saying, but essentially what it's saying is that if you multiply by x to the power m any power series, then what it results is converging to x to the power m times f of x, because after all this series, this much converges to f of x. So a multiplication by x to the power m in front will result in x to the power m times f of x. The next one is the composition. So suppose you have b times x to the power m is a function h of x. Then if you take the power series and instead of x you write h of x, then it converges to the composite function f of h of x. So what it basically said is this. So suppose you have a power series ck x to the power k, and this converges to the function f of x. So now instead of x, suppose you write x cube. So that means ck x cube raised to the power k. Where will this converge to? Well, it will converge to f of x cube, because where you saw x you wrote x cube, so here on this side you will have x cube. You will see the application of it in few minutes. Okay, so first thing is that we know these two results. I just talked about this one. This comes from geometric series, and similarly this one comes from geometric series. So if you have a power series -1 raised to the power n x to the power n, it converges to 1 over 1 plus x. If you have just x to the power n, it converges to 1 over 1 minus x. So the first question is, find the power series representation of the following functions. So suppose somebody gives us a function 2 over 1 minus x squared. So 2 over 1 minus x squared could be written as 2 over 1 plus x times 1 minus x. You can factor the denominator. Now this from partial fractions can be written as 1 over 1 plus x plus 1 over 1 minus x. Very simple. You can check. By adding these two, you will see that it comes to 2 over 1 plus x, 1 minus x. Now I know the power series of this. So the power series of this is -1 to the power n x to the power n. The power series for this is simply x to the power n. So now we have to learn how to combine these two series. So one way to do it is by writing them out. So I'm going to do it that way, and then you can become comfortable doing it without writing it also. So first let's do when n is equal to 0. So when it's 0, I get 1 from here and plus 1 from here. Okay, then n is 1. So these are all added, so this is 1 plus 1. So when n is 1, I get from here -1 to the power 1 and x to the power 1, so I get -x, and this one gives me plus x. Then n is 2. So when n is 2, -1 squared x squared, so that is x squared, and then x squared. When n is 3, I get plus -x cube plus x cube, and so on. So clearly there's a pattern. The first one I get 1 plus 1 is 2. Then this cancels each other, so the odd power minus x and x go away. And then the next one is, so plus 0 plus 2x squared plus 0 plus 2x to the power 4, and so on. So what I have here is, I can factor out 2, and I get 1 plus x squared plus x to the power 4 plus x to the power 6, and so on. So this can be written as 2 times summation x to the power 2n, n going from 0 to infinity. So this is the answer if you go and do it this way. Now we can do the same question another way. So I want to write the power series of this. So the trick here is to see who is this similar to. Now this is very similar to this one. So what I'm saying is series xn is 1 over 1 minus x. Now 2 over 1 minus x squared and 1 over 1 minus x are very similar. So I need a 2 here instead of 1, and instead of x I need x squared instead of x. So look at this power series. So I need a 2. So I'll write 2 summation. Now if I want x squared instead of x, so then here I'm going to write x squared. This is the composition. So I'll write x squared and then obviously raised to the power n. And that is 2 times summation x to the power 2n. So that is the answer. This is obviously exactly same as the previous way but much faster. Let's go to the next one. So x to the power 4 over 1 minus x. So this is very simple. It just means x to the power 4 times 1 over 1 minus x. Now 1 over 1 minus x, x to the power 4 is same. 1 over 1 minus x can be written in its power series representation, and that is simply x to the power n. So it's x to the power 4 times this. So every term of this is going to get multiplied by x to the power 4. So we can bring x to the power 4 inside the summation, and I would get this. So that's the answer. So suppose I want to do this. Now we know that 1 over 1 minus x is summation x to the power n. So now here I see x to the power 4. So wherever I see x, I'm going to write x to the power 4. So it would be summation. Now when it was 1 over 1 minus x, you had x to the power n. Now I have 1 over 1 minus x to the power 4. So I'll write x to the power 4 and then raise it to the power n. So instead of x, I have x to the power 4. So this is the composition we were talking about. So therefore the answer is summation x to the power 4n. So this is the answer. So I can make up another example. Suppose we want to find x cube over 1 plus x cube. So what you can do is keep x cube and then you have 1 over 1 plus x cube. Now let's look at the power series of 1 over 1 plus x. That was negative 1 to the power n x to the power n. So now see the similarity between this and this. So x cube stays, and for this I had x, now I need x cube, so I'm gonna put x cube here. X cube raised to the power n. Now when x cube gets multiplied here, I have negative 1 to the power n. This is x3n, x raised to the power 3n, and then a 3 is coming from here, so plus 3. So your final answer would be this. Okay. Now we go to the application of power series by differentiating and integrating. So what this theorem says is that suppose a power series converges for this interval and defines a function f on that interval. That means it converges to f. Okay, so then f is differentiable, so it is if this is the function f, then it is differentiable, and you can find f prime by taking the derivative of each term of this power series, and that's what this is. K, what's the derivative of this? Ck stays ck, k comes in front, so you get k, x minus a raised to the power k minus 1. And similarly, you could do the integration as well. Again, as usual, the best way to understand these things is by doing an example. So I want to find the power series of log of 1 minus x. So observe one thing, that if I integrate 1 over 1 minus x, then I get negative ln of 1 minus x. That's a simple u substitution, and you would get this. So this implies that log of 1 minus x is minus integral of 1 over 1 minus x dx. We know the power series of 1 over 1 minus x, and that is 1 plus x squared plus x cubed, and so on. So if I want to find this, all that I have to do is integrate this. But integrating this means all that I have to do is integrate this power series. This is exactly what this is saying. So therefore ln of 1 minus x is minus coming from here, integral of this function, but this function can be written as a power series, so it becomes integral of 1 plus x squared plus x cubed, and so on, dx. So I would get negative integral of 1 is x, next one is x squared over 2 plus x cubed over 3 plus x4 over 4, and so on. Now clearly there is a pattern, and that would be negative summation x. Now since n starts from 0 and I want my first term to be x, this would be n plus 1, because when n is 0 I get x, and then when n is 1 I'll get x raised to the power 2, but then I need a 2 in the denominator, so I have to divide it by n plus 1. So you can start with 0, you will get x, you put n as 1, you will get x squared over 2, you put n as 2, you would get x cubed over 3, and so on till infinity. So therefore the power series of log of 1 minus x is this term. Similarly, for tangent inverse x, now we know that integral of 1 over 1 plus x squared dx is tangent inverse x. But then we know the power series for 1 over 1 plus x squared. So that means integral of summation of negative 1 to the power n x to the power 2n dx. Let me remind you, so we know 1 over 1 plus x is summation minus 1 to the power n x to the power n. Therefore 1 over 1 plus x squared would be, substitute x squared for x and you get x squared, and then raise it to the power n. So that's what I've written here. So this means integration, and now let's write out few terms. So start with 0, so I have 1, then let's put n as 1, so I'll get minus, because minus 1 to the power 1, and then x to the power 2 times 1, so minus x squared. Then n is 2, so I'll get plus x to the power 4, then minus x to the power 6, plus, and so on. So now let's integrate this. So when I integrate 1, I get x, then I get minus x cubed over 3, then plus x5 over 5, minus x7 over 7, and so on. So first thing to notice is that this is alternating, so it has to be negative 1 raised to the power n. N starts from 0. Then I need odd powers, so x, x cubed, x5, x7. So you would say x raised to the power 2n plus 1 divided by 2n plus 1. So you can check, when n is 0 you get plus, and here you would get x over 1, so you got this term. Then you put n as 1, then you would get a negative sign, and x 2 plus 1, 3 over 3, so x cubed over 3. Then when n is 2, you would get x 5 over 5, so this is your power series for tangent inverse x. So this is a very powerful technique of generating power series for various functions through integration or through differentiation.